Okay. So let me start. This session will deal with jets in common envelope evolution, and those who do not know me, my name actually doesn't sound like pleasantness review, but if you translate each name, Noam and Soker separately, it's pleasantness review, but it is definitely not going to be a review and more definitely not going to be pleasant. So let's start. So the problem in common envelope from observational point of view, we cannot see jets and let them break out, but then we need to interpret it that it was the jet were inside the common envelope. In other cases where we can see, we see jet. And here I show you a cluster of galaxies. This cluster of galaxies is very famous because the central black hole is 10 to the 10 solar masses. In red here, you see the radio jet. You see it has an S shape. It is precessing. In blue, you see the X-ray gas, and the jet displays the X-ray gas, and you see on the upper right, only the X-ray, you see these two lobes, a kind of bipolar structure, which we know from planetary nebulae, and in white, you see all the galaxies. And here you see it again, but look at the blue upper right of the cluster of galaxies. This is X-ray, and above it in white, you see a low resolution image of a planetary nebula, Hubble 5. On the left side, you see the high resolution. Again, you see the S shape. It's not a galaxy yet, but it's point symmetric. And the image of the X-ray of the image in the X-ray of the cluster of galaxies is very similar to the low resolution optical image of a planetary nebula, which high resolution, you can see many, many details. So, and in cluster, we know the X-ray is displaced and shaped by jets, so why not in planetary nebulae? This is, you can read by yourself. This, we think it's a luminous red nova, ILOT, I call it, it doesn't matter, interaction of two stars. And again, you see the clear S shape, and I pointed it out in Slack. This is by Tommy Kaminsky and collaborators, some of whom participate in this meeting. So this S shape also suggests to me that the eruption was powered by jets. I mean, accretion channel two opposite jets that power the luminous radiation. We can go to a planetary nebula where we see a ring. You see this clumpy ring. On the upper left and upper right of each image, it's just different lines. You see the jets. You see jets that shape the nebula. Now we see only the jets going to the upper left and lower right and the ring. And if you look at supernova 87A on the lower left, you see also central ring and upper and lower larger ring. On the right-hand side, you see something similar, which is the planetary nebula. You see several rings, but again, in a two opposite sides, kind of an hourglass. And this ring that I showed before is very similar to the ring of supernova 87A. On the left side, you see supernova 87A. Again, clumpy ring. Look, in the inner part, you see the explosion and how it was 15 years ago. You see asymmetrical explosion. And you see the ring, and I think it also was shaped by jets. Let's go back to this planetary nebula, a very famous one, and I have the credit here. You see an hourglass shape and several rings, and if you look at the same planetary nebula, but much wider field and deeper, you see the jets. This kind of hourglass shape that we might, old models say that the hourglass was collimated by the dense equatorial material. But if we see the jets, I don't think this is the best scenario. And you see a little bit S-shape here. I mean, not really sharp, but you see it. Okay, let's go back now to jets in a common envelope evolution. We cannot see the jets, but why not the companion? We launch jets at the binary progenitor of planetary nebulae, some before the common envelope, some after. So I think white dwarfs have a hard time to launch very strong jets. They can launch jets, but not strong enough to play a major role in a common envelope evolution. But neutron star, black holes, and main sequence star can. In particular, neutron star and black holes because of neutrino cooling. In the case of main sequence star and also neutron star and black holes, the jets themselves can also remove energy and allow accretion at a high rate, and we will hear about it in the coming session. Luke Chamandi and collaborators pointed this out as well. So the point with neutron star and black hole, which many of us were not used to because we always looked at planetary nebulae and CVs and so on, where the companion was mainly main sequence, sometimes white dwarf. The process is simply that you form at high temperature very large number of neutrino, anti-neutrino pairs, which just carry the energy out. And this allows accretion at a high rate. And the neutrino cooling is very sensitive to temperature. So when you accrete to a compact object like neutron star or black hole, you can have a very efficient cooling, which allows accretion at a high rate, but the angular momentum is there. And the compact object in the common envelope accretes from a non-homogeneous medium because the density in the part inner to the orbit is higher than the density in the outer part, and this causes accretion of large amount of angular momentum with this accretion, and also we will hear about it in this session. Okay, so what about the accretion rate? And we will hear it all about it also in this session, but let me give just an introduction to it. So the accretion rate, when we include jets, include two factors. M dot Bondi-Hoyle-Littleton 0 refers to the accretion rate that the analytical formula of Bondi-Hoyle-Littleton gives in the unperturbed envelope. Now there are two factors. Xi stands for the decrease in the accretion rate because of the pressure gradient and the density gradient that comes with it and so on. It leads to lower mass accretion rate than the typical or analytical Bondi-Hoyle-Littleton. Then the jets themselves remove mass, as Chamandi et al. Also discussed it in the model of jet, because they inflate low density material around, and we will hear about it later here. So the outcome is that we have a lower mass accretion rate. And Xi, I take this number as 0.1 to 0.5. In some cases, it can be 1. Some people claim it's less than 0.1. This is dispute, which is fine. The effect of the jet is under study. Our group studied in simple manners as of this time, and we will hear about it later today. What is the power of the jet? So not all the accretion power go to jet. Most of it goes to neutrino cooling. But a fraction of 5, 10, maybe 20% goes to jet, and call it eta. So in this formula, the power of the jet is 10% of the accretion power, and you need to get the accretion power is the accretion rate times the potential well of the accretor. It could be a neutron star, black hole, or this formula does not refer to main sequence star because of the eta. So if a neutron star or black hole spirals inside the envelope and then in the core, they can accrete mass and launch very energetic jets. Did we see, or not directly, we cannot see the jet directly, but do we have indications for this process? So before that, because we deal here also with the case of the neutron star, black hole, or main sequence star, white dwarf, enter the envelope and reaches the core, we must also consider the case, and then we'll comment on it in 3 minutes, of the outcome of merger of the compact object with the core. But even if we don't get merger, when it comes very close, we should consider the possibility of what I call migration, because we have a circumbinary disk that form around the binaries, and it's like planet migration around young stellar object. And so this circumbinary disk can further cause the binary, now the compact companion and the core, to spiral in, And this process can lead to more merger than we would expect otherwise. Okay. In other cases, we have the grazing envelope evolution, where you see on the right side that the companion with the jets remove the gas and stay the system is semi-detached, or just the companion grazes the envelope, and we heard about it from Sagiv Shiber already. So let us talk about the class of supernova progenitors that result from fatal common envelope evolution. Some people say merger, but merger is not well defined, because some people, when they say merger, they mean that the companion and the giant merge. Some, when they say merger, mean that the companion and the core merge. So to prevent any confusion, I call the case of the companion merging with the core as a fatal common envelope evolution, because either the companion will be destroyed, like if it's a brown dwarf, it can be destroyed by the core of an AGB star. But if it is a neutron star, it will destroy the core of a red supergiant star. So we have kind of fatal common envelope evolution. There are too many scenarios. It will be on the recording. I only mentioned some of them to give you just taste of what is going on. One possibility is CO white dwarf merging with a helium CO core or with a CO core, leading to a more massive white dwarf that might explode during the common envelope, shortly after or long time after. This is a core white dwarf merger. Haji Ablimit had a talk on that when he also mentioned magnesium neon white dwarf. And we had this Anders talk about supernova 2006 GY, which he proposed also the core degenerate scenario. This is a core degenerate scenario. Another case is a common envelope jet supernova that I mentioned. If the neutron star enters the core, accretes mass at a very high rate and launches the jets. So in some cases, it doesn't get to the core, it ejects all the envelope. In this case, we call it imposters because it's not really get to the core, it does not destroy the core, and the core later can explode as a supernova. So the neutron star actually destroys the core, or it can be a black hole or neutron star. The black hole neutron star destroys the core, forms an accretion disk because of angular momentum that launches very energetic jet, and nuclear reaction can take place here, as Yosef Zenati, Chagai Peretz mentioned in some of the papers. So did we see any of these? So we had several suggestions for this type of object of common envelope jet supernovae with Avishai Gilkis. We propose IPTF 14 HLS, which is a very enigmatic supernova. And with Aldana Grichiner and Avishai Gilkis, we discussed several scenarios. One of them account for this supernova, the cow, which is also a very enigmatic supernova. And you have the link here. I'm sure you're going to read it tonight. Are these two examples the only one? No. Here you find the news release from 2nd of September 2021. So this was yesterday. The paper is actually from today, so it was released yesterday, and they say theorists have predicted this. They talked about jets from a neutron star or black hole getting into a core of a star. Theorists had predicted this could happen, but this is the first time we have actually seen such an event. I disagree. I pointed you out two earlier events that also were suggested to be the common envelope jet supernova event. But in order to publish it in Science and the press release, you need to have it. So this is not on the main journal in astrophysics, AstroPH, and this is not there. And I think that informing reporters before the professional community is politics. It is not the way to do science. My view that it is unethical. I'm unhappy about it, but their system that they observe, I count as another example of a common envelope jet supernova, though they have another name to this scenario. I will end with another outcome of fatal common envelope evolution, and you have here blue giant progenitor with main sequence star that gets inside and it can be ejected all the envelope and then if by itself be distracted and form of a low mass envelope. It can be type 2b. This is not the main scenario, maybe for type 2b, but one of them. Other scenario involve type 1b and c core collapse supernovae. We have the case of two giant that merge and can form like a regular core collapse supernovae, but very heavy circumstellar medium. And there is a reverse evolution where you have a wide dwarf spirals in and later on form a supernova. But I will not get all this. It's not my talk. This is my my last point. I will finish here and we'll leave 4 minutes for some question and then we go to the scheduled talk. Yes, please. Any comments or?
Noam, I have a question,
Yes.
comment.
Yes.
So I mean, I think it's a right. I mean, we've also seen in our own work that you may need, a neutron star sort of to power to really disrupt, to do serious damage to the envelope. But of course, that means that for planetary nebula, then it's not clear how much what effect the jets will actually have. I mean, I think that's kind of an ongoing. I mean, once you get in, once you've plunged in.
You mean when you have a main sequence companion?
Main sequence and maybe even white dwarf. I mean, I think would
Yeah,
agree that question is still open to see what.
So yeah, I agree with you. I think main sequence have most of the effect on the planetary nebula before and after the common envelope. Yeah.
Right. Okay.
Yes. Okay. Raishko? Rai, please.
Yeah, I had a kind of similar question. So can you briefly comment on how, so you mentioned the main sequence stars can also create jets, but what kind of mechanism causes main sequence stars to have jets? I can understand the neutrino cooling for the neutron stars and black holes, but I can't picture how the jet driving works for main sequence stars.
I think main sequence it is more difficult, maybe much more difficult to form an accretion disk and jets by a main sequence. I think if it doesn't have a disk when it enters the envelope, it will not have it in general. So I would argue that we need the main sequence star to have an accretion disk and jets when it already enters the envelope. And then it can experience either the grazing envelope evolution or enter the envelope and with the jets that will help expel the envelope. But maybe the jet will die and appear later after it ejected the envelope, and maybe there is a circumbinary disk similar to system that Hans van Winkel studied. And I see Hans is here; he might comment into that. I don't know.
Yeah, I will illustrate that in my talk later.
Okay, very good, very good.
On
yes.
the jet properties around main sequence stars.
Great.
But you need a feeding mechanism.
Yeah, of course. The feeding can come from a circumbinary disk, as in your case. After the common envelope evolution, if we have jet, it's much more similar to your case than to Roche lobe overflow. Yes.
Yep.
Yes. Okay. Adam, you have more questions or answers?
Well, just no answers. Just that question of the cases afterwards. I mean, Hans, for your systems, those disks are pretty big, right? Do we really have the densities in those disks enough that we could power the jets? I'm not remembering.
No, but the jet is powered by the accretion disk around the companion that is fed by mass from the circumbinary disk.
Okay, all right, right. So it's secondary, right? The mass is feeding. So you're able to concentrate the mass from into the the disk around the companion from the mass from the. Okay.
Yeah.
So that's
Okay,
got it.
Aldana, please share your screen. We will continue with the question, but you can say yes. Alexei, I saw your raised hand.
Raise the hand for 1 second. So yeah, so I was curious. I mean, so if you think about neutron stars and post-common envelope binaries launching jets, right? So that probably can be correlated somehow to accretion onto neutron stars and them being observed as recycled or non-recycled pulsars after that. Has anybody tried to do a study of whether recycledness of pulsars post-common envelope can connect to this picture? In other words, if you have a neutron star launching jet, probably it's accreting material. If it's accreting material, probably it's getting spun up. If it's getting spun up, it's turning into weak magnetic recycled rapidly spinning pulsar. And we have observations of those on short periods.
No, I didn't look on spinning up in the common envelope to explain this recycled. We looked at spinning up in other regards, like forming what will be the spin after the common envelope. So in what I showed yesterday in triple star, we looked on the accretion to form misaligned orbit, spin orbit misalignment. So this is something else. Enrique?
Yes, so thinking about what was commented just a second ago, so I think it would be also hard to find the ejected material, since these systems tend to be very, very old, because the recycling allows them to be pulsars for billions of years. So all that material that you might have removed through the common envelope or something like that might be long gone.
Okay. So Aldana, please share your screen. So the next speaker is Aldana. She is my PhD student. So the talk will be 2 hours. Please don't leave.
Okay, do you see my screen?
Yes.
Okay, so hello, my name is Aldana, and today I'm going to discuss high energy neutrino emission from jets in common envelope evolution. So first, when I describe high energy neutrinos, what do I mean? In 2013, the IceCube Neutrino Observatory detected neutrinos with energies up to 10 to the 15 electron volt. Actually, when we look at neutrinos that come from supernova explosions, we see that it can reach about 10 to the 6 and to the 7 electron volt, meaning that there is a huge order of magnitude difference between these energies. We actually don't know where these neutrinos are produced. We know that their arrival directions are compatible with anisotropic flux, implying that there is no indication of a concentration towards either the galactic center nor the galactic plane. This actually strongly suggests that the high energy neutrino flux is from an extragalactic origin, even though it does not have any significant correlation with any class of extragalactic object so far. So we don't know where these neutrinos are produced, but we believe that we know how they're produced, what is the mechanism of their productions. And this mechanism implies very energetic protons that we will regard as cosmic rays that actually they collide with some very thermal photons in their surroundings. So when they collide, they produce pions that could be neutral or uncharged, or charged pions. So the charged pions, they will decay into muons or electrons, emitting neutrinos in the process, while the uncharged pions will actually decay to gamma rays. So the problem with that is that if the charged pions decay, uncharged pions decay to gamma rays, and as you can see that in high energy, all pions are produced. So every event of high energy neutrino emission must be accompanied by the production of energetic gamma rays. Yet we do not detect these gamma rays by the Fermi telescope, which implies that the source of high energy neutrinos should be of an optically thick origin. So actually, in order for a source to be considered as an high energy neutrino source, it should fulfill these 3 requirements. It should be an extragalactic source in order to account for the isotropic flux. It should have a viable mechanism for the acceleration of cosmic rays to explain the neutrino energies, and it should be optically thick to gamma radiation to explain the non-correlation between the Fermi and the high energy neutrino flux. So we believe that these neutrinos can be formed in a mechanism called common envelope jet supernovae, which is a system that Noam and Muhammad discussed earlier. Briefly, a common envelope jet supernovae is an event in which a neutron star or a black hole companion are engulfed by a red supergiant. When they're engulfed, they actually launch jets inside the envelope and later inside the core of the red supergiant through an accretion disk that is formed. The compact object spirals inside the red supergiant, and when it reaches the core, it launches very energetic jets that collide with the core and destruct it in an explosion that might resemble a core collapse supernova explosion, and hence the name common envelope jet supernovae. So these kinds of systems begin with two main sequence stars. They are both massive, when one of them is heavier than the other. So the heavier star evolves into a red supergiant, but in this phase there is a possible mass transfer from the main sequence star to the red supergiant, yet the main sequence star is massive enough in order to maintain synchronization and prevent the onset of a common envelope evolution at this stage. So the red supergiant keeps evolving and explodes as a supernova, leaving a black hole behind. And if enough mass remains bound to the system, we end up with a binary system of a main sequence star and a black hole, when the main sequence star that is heavy to begin with evolves into a red supergiant that can engulf the black hole that spirals inside its envelope, initiating a common envelope evolution phase. So we believe that in this phase, there is an accretion disk that is formed around the black hole, and the accretion disk launches relativistic jets that are collimated by the envelope material. So inside these jets, we have protons that are accelerated to very high energies due to the strong magnetic field inside the jets, because they are scattered across the Schoff interface. And in these jets, these pions can be produced, emitting gamma rays and neutrinos. And while the high energy neutrinos could stream out freely due to their low cross-section for interaction with regular material, the gamma rays would remain trapped inside the optically thick envelope in the case where the jets remain stalled inside the envelope. So this is a nice idea, but we need to actually show that common envelope jet supernovae with black hole companions can fulfill at least these three source requirements. So as for the extra galactic source, there is actually no favoritism for our Milky Way in order to produce common envelope jet supernovae, so it's kind of a given. And now I will focus on the rest of the talk on these two remaining criteria. So in order to test our model, we use the stellar evolution code named MESA, and we evolved a 30 solar massive star from the zero-H-band sequence until it reaches a radius of about 1,000 solar radii. At this point, we assume that a black hole of 3 solar masses is swallowed by the red supergiant, and since the moment that the black hole is swallowed, it starts launching jets that deposit their energy inside the envelope of the red supergiant. So we deposit the jet's energy using the efficiency parameter of 0.1 and assuming a mass accretion rate, which is about 10% the Bondi-Littleton mass accretion rate. We take the orbital separation between the black hole and the core of the red supergiant at any time from the simulations of Schroeder et al. In 2020. We conduct hydrodynamical simulation of such systems with these masses, and we follow the spiraling in of the black hole until it reaches an orbital separation of 100 solar radii after 3 years. So we can see that an extended envelope is formed around the system of a black hole and core. So we take our stellar profiles in order to see what is the maximum cosmic ray energy that our scenario can give. In order to do this, we compute the acceleration time scale of the protons in the comobium frame, meaning in the jet's rest frame, and we compare it with the typical cooling time scale in the system. In the temperatures that we are dealing with, the leading cooling process is P gamma interactions, meaning interaction of the accelerated protons with thermal photons that arise from the jet head and diffuse into the region of the protons. And we know that as long as the acceleration timescale is smaller than the cooling timescale, the protons would keep being accelerated. So then, by equating these two timescales, we find that the maximum energy that our cosmic rays can reach is about 4 times 10 to the 16 electron volt, while the accurate value depends on the magnetic field of the jets in the moving frame, on the temperature of the photons that interact with the protons, and with on the gamma factor, the Lorentz factor in our model. And since neutrinos can take about 5% of the energy of the cosmic rays, we can see that our model can pretty much explain the energies of the neutrinos that were produced in IceCube. So now we only need to show that our tool requirement is fulfilled. In order to do this, we have two stages. First, we need to show that the jets remain stored inside the envelope, because if they break out, the gamma ray would be visible. And after that, in case where the jets remain stored, we need to show that the envelope is optically thick enough to retain the gamma rays inside. So first, we compute the breakout luminosity of one jet, which implies that is the luminosity that a jet must have in order to break out from the envelope. And we compare it with the typical luminosity of one jet, which is drawn here with the magenta line. So we can see from this plot that for most of the orbital separations that we investigated, the breakout luminosity is several order of magnitudes above the typical luminosity of one jet, what implies that the jets would remain stalled inside the envelope. And this is good. And afterwards, we take the calculations of Muras et al. From 2016, which says that a high energy neutrino source should be opaque to 1 to 100 GeV gamma rays. And we compute the optical depth along the propagation line of the jet, which is perpendicular to the orbital plane. So we know that the leading process in this matter is pair production, and we compute the optical depth for 1 GeV gamma rays. The opacity goes up with the energy. This is sufficient to prove our point. And as we can see, in the vast majority of the envelope is optically thick, implying that it can retain the gamma rays inside. So we actually showed that our common envelope jet supernova scenario can fulfill these two requirements, which means it might be a possible and promising source of high energy neutrinos. And now we're working on extending the work by sparing in of the black hole to even deeper radii and see if we can better match observations. So I'm done. Thank you very much.
Okay, we have time for 47 questions, please. Yes, Morgan.
Hi, thanks so much for this really fantastic presentation. I wanted to ask you about how a common envelope jet supernova might differ from, say, that same like donor star or progenitor in a like collapsar scenario. So I'm thinking like the Dexter paper about the core of a very extended star collapsing and then like long-term accretion. Do you think we could distinguish those? What are the differences? What are the similarities? Yeah.
So one of the differences is that in the collapsar scenario, the jets arise from the central object, the center of the star. And in our case, we have a spiraling in black hole that launches jets in its trajectory inside the common envelope. So I think that would be a different characteristic because we need to consider spiraling time. Maybe the time scales would be different in this respect. And this is one of the ways we can distinguish. I don't know how we can distinguish this observationally. Maybe, I don't know, maybe by calculating the gravitational wave emission that should come from each one, or maybe looking at the light curve of these events as Noam mentioned before, maybe we'll mention afterwards, there think that common envelope jet supernovae can, due to the operation of the jets, can lead to very distinguished light curves, maybe many peaks, light curves of many peaks. So because the operation of the jets is not continuous, I think the collapse rate must be more continuous than in this case.
And then also
that would be really interesting.
Accretion rate cannot be too high according to your calculations.
Yeah, so
Right.
in our case, the accretion rate in order to produce high energy neutrinos can be too high, because in the case it's too high, we have radiation mediated shocks, and this can suppress the acceleration of cosmic rays.
Oh, that must be extremely important, because then the fact that you're kind of coming from the outside in, from low density to higher density, kind of seems central to that story. Is that right?
Yeah, because if we are inside the core, we find that high energy neutrinos won't be produced due to the very high luminosity of the jets inside the core, very high power.
Right. That's amazing.
So
thanks.
we wanted to explore it a little down, more down inside the envelope, but we know that we cannot reach the core in this scenario.
Okay. Eli, please.
So in order to launch a jet inside the common envelope, I guess you need neutrino cooling there, like in the disk, well, to form a disk in the first place, right? So would you so you're creating a high energy neutrinos at the jet head, but you're also creating low energy neutrinos in the disk. And would you expect you always have a simultaneous super Kamikaze detection every time you have a high energy ice cube detection in this model?
This is actually a very interesting point. I actually didn't think about this far. I suppose yes. Now, what do you think?
Yeah, we should consider it. If we have neutrino cooling, we should have flux, but we didn't look.
I think that around a black hole, maybe there is less neutrino cooling than around the neutron star, because many of the energy is dissipated through the horizon.
We still need to have, but there might be a lower energy if the cooling is outside. It's something to calculate, really. It's a good question.
Yeah, I mean, I think you may even be able to use the super Kamikaze upper limits or something to just constrain, rates or something for your model, for your scenario.
Okay. Yeah, it's a good point.
It's a very good point. Thank you.
Adam.
I was just struck me that also a big difference may be that the density profile that the jet is, or that the supernova eventually is going to have to propagate through, because you will have carved out the chord apple. By the time you get to supernova, if I understand correctly, you will already had a fair amount of common envelope evolution, so you'll get the chord apple density distribution for the circumstellar, or the whatever, the envelope of the star, so that the light curve should look different, and the supernova propagation will look different, because it'll blow through the polar regions much quicker than it blows through the equatorial. So I would think that would actually have, because there's quite a rate, we know common envelope evolution shapes the envelope quite dramatically. So once the explosion happens, it's moving into a very different medium. That just strikes me as a comment, not a question. Sorry.
Depends on the delay time from the supernova, from the common envelope to the supernova. In 87.8 it was 20,000 years. It's not black hole. Yeah. Dana, you want to add something?
Chagai has a question.
Yeah, Chagai.
Yeah, so I want to raise a general question. I already raised it to Adana and Noam, of course, beforehand, but in general, I think we need to ask not just about this, but in general about ejecting jets and accretion in common envelope, whether it's really so efficient. First of all, I mean, all of this was really depending on the assumption on the accretion efficiency. You took 10%, as you know, this is pretty sensitive. If you took 1% instead, all of this would not work, for example. And it's not very clear to me that the accretion is so efficient, especially if you form an accretion disk. It means that you have the viscous timescale, right, for accretion in the inner parts. This is a much longer time than just general. No, it's enough time potentially to actually propagate the information backwards and actually not allow for a simple Bondi-Hoyle Littleton accretion. So if it's on a kind of direct collapse or direct into the compact object, you don't have any time, and then you can continue it. But if you have more time for that, then you can actually have a backward propagation of that, and you produce pressure, and you might not allow for further accretion. So it's not very clear to me that Bondi-Hoyle accretion, a simple Bondi-Hoyle accretion, really is appropriate when the scale of the accretion is so much larger than the scale where the energy is actually dissipated, in this case by neutrino field. I think it's a general question, not just for Aldana, of course, and I think we should actually raise it in the discussions in the session.
And so just one comment to this question, to what I said at the beginning. It's not so clear to me that if we take a 1% accretion rate instead of 10% accretion rate, the model wouldn't work, because as I can show in the graph before, we only explore what happens down to 100 solar radii to do the resolution of the simulation of Schroeder et al. So if we go deeper into the envelope, we have a lower accretion rate, we can still have shocks that are not mediated by radiation, but still an accretion rate that is high enough in order to account for the calculation we made so far. So it's not that the whole model falls down on this percentage of the accretion rate in this case. This is what I believe. But, but I agree that the question.
Yeah, but you haven't tested it, and your whole model is also inside MESA and not a real simulation. So there are many other things on the way through. If you try to kind of extrapolate left further on, I'll say you need to do many more steps beforehand, and in order to actually check these issues. So it is possible. I'm saying it's not very clear to me. I think it needs to be studied much deeper to understand what kind of accretion do you have and the formation of jet in these kind of cases. Because if you just assume all of this, then there are many other processes can happen if you have such efficient accretion. Not in this common envelope, but also in common envelope. And I think you have many ramifications, not just for these ideas that you mentioned. And these could probably constrain through observation in many ways. So at least I'm at least a bit worried about these for me, extremely high accretion rates. That's all.
Minhaji, please. Minhaji, are you with us? No, I don't know. Morgan, please go ahead.
So I wanted to raise kind of an amazing transient that was reported in the September 3 Science, so today. And what they saw was high energy transient, GRB, and then in 2014, and then radio emission more recently. And the claim is that this is associated with something like a merger-driven supernova, common envelope jet supernova. And so that's a case where the jet was penetrating out of the envelope because they saw beamed emission. And also sort of interesting is that there are limits on the optical. And so they didn't see an optical supernova. And so I think this comes back to Noam's point about the delay time. So somehow there was an explosion such that there wasn't material at 10 to the 15 centimeters, as for example, we were predicting in the Schroeder paper, but there was at 10 to the 17 centimeters that's driving the radio afterglow. So I guess I wondered if you could talk a little bit about what we might need to have happen to have a slightly clearer immediate surrounding, and whether that's what would we need to have happen for the jet to penetrate out, like sort of the opposite of the sort of ratios of luminosities that you were talking about in this particular example, and whether that pertains to how we can understand this source.
If I understand correctly, you ask how we deduce when a jet breakouts and when it remains inside the envelope?
Yeah, in a sense, and I mean, I think we have an observation of the opposite scenario. And so what does that tell us about that particular source? And
so we actually compare the two time scales in order to perform our calculations here. The breakout time scale of the jet, meaning the time it takes the jets to reach the envelope, and the crossing, typical crossing time of the black hole are in its Keplerian motion are inside the envelope. So we actually follow the calculation of Bromberg et al. In 2011 in order to compute what would be the breakout time, and but instead of comparing it to the typical time scale of the source, we compare it to a time scale of one particular jet that would be launched from the black hole in our system.
Aldana, can you stop your share?
Yeah. I stopped it.
Okay, so I want to answer the question of Morgan, and then we go to Iman Haji. I show you a paper of diversity of common enveloped supernovae. This by Aldana Gwichner and Avishai Gilkis and myself, and I mentioned it in my talk, in my opening talk. So we have what we call is polar common envelope jet supernovae, which is a pre-explosion envelope. It's a low mass, highly oblate, empty pores. So in this case, what has happened, the jet expand and actually do not collide with much material. I don't know how much. This depends on the evolution. So we did, when we discussed a different kind of common envelope jet supernova evolution, we did discuss the polar common envelope jet supernova, where the jet expand out and less interact. We wanted to expand the blue, the rapidly decaying enigmatic supernova 2018 cow. So I think we should discuss it later, but there are possibilities that we already mentioned, but we didn't go deep into it. This object might promote further evolution of the polar common envelope jet supernova. Okay, Imnaji asked.
Oh, I think there's a lot of parallels. Yeah, that's a really nice comparison. Thanks.
Yes, I don't know if you saw my opening remark that their object is not the first, but the third one to be classified as common, not classified, suggested to be common envelope jet supernova.
Right.
So we had before the IPTF 14 HLS and this one. Iminaji asked you, Aldana, about the relation between gamma ray burst and the common envelope jet supernova, if you want to say something.
And the relation or the comparison?
It's general comparison, or if it can be also a source of gamma ray burst.
So the difference between our common envelope jet supernova and the gamma ray burst, that the jet in the gamma ray burst emerges from the central object in the middle of the star, while, as Morgan pointed out earlier, in our case, the black hole, the neutron star, they come from the outside and spiraling inside the envelope, and they're not continuous. We have a much longer time scale for the launching of the jets. Maybe can reach up to several years compared to gamma ray burst.
Yeah, there are several differences, like the jets do not go out in most cases in common envelope jet supernova, but Roger Chevalier mentioned the possibilities of common envelope jet supernova. I didn't call it, he mentioned it, I think, in 2012, that might be some gamma ray burst, might be due to this process. Diego, please share your screen. We must continue on, and there will be discussion at the end of the day. Aldana, thank you very much. Diego, please.
Yeah. Okay. So, hi everyone. My name is Diego Lopez Cámara. I'm a researcher at the Instituto de Astronomía at the UNAM. And this paper project that I'm going to talk about is in collaboration with Fabio De Colle, that's also at UNAM, and Enrique Moreno Mendez that talked yesterday. And we joined forces with Sagiv, that also talked 2 days ago, and Roberto Iaconi. Great. So I guess we pretty much all know that there's still an open place for jets. I mean, apart from all these driving mechanisms that have been discussed in the past, the famous alpha mechanism that we like less and less, and it goes down up to this beautiful study that Fritz showed us yesterday. And I don't know, I mean, thing is, all of these tend to have difficulties ending the common envelope phase, and thus there is room for jets as a extra energy source, or even as the main driving energy source. And this figure, actually, Aldana showed it just a few minutes ago. Okay, so also what I want to show is that, so there's large-scale simulations that we've already discussed, and small-scale simulations. This is the simulation that Sagiv showed 2 days ago. And the pros, of course, is that we can see the global behavior of the common envelope. The problem is, yes, we have resolution problems, especially near the secondary, where it's launching a jet, or it's also difficult to solve small opening angles. Of course, as we've seen, it's difficult to follow the accretion, and as we've Ryosuke actually pointed out, now again, how is the disk formed? On the other hand, so we have small-scale simulations. Nice thing here is we can see all these, jet open angle, the accretion, maybe even disk formation. The con is that we only see a small fraction of the whole domain of the whole problem that we want to analyze. And another thing that is also quite hard, well, that I don't like, is that you're not able to solve large times, and you have to, well, you're Nimodel. You have to do small scale times, and you can't see these beautiful tidal tails that Morgan showed a few days ago. And of course, we're not pretty sure if we can really stop the common envelope. Okay, but what I want to show you here is that, so in this study, we are actually joining forces between large scale and small scale simulation. And the way that this happened is, as Sagiv pointed out in his study with Roberto, they said that they have, when jets are included, there's 3 more times the amount of unbound mass, and also the flow morphology is bipolar. And that's when Fabio, Enrique, and I said, is this really so? Does this really happen when you have, like, when you're able to solve everything that's happening close to this secondary star that's launching the jet and that's accreting material? And another thing is, unlike in Sagiv's and Roberto's study, they launch constant jets. And we had been analyzing what happens with self-regulated jets. So this is how much material is accreted, and then you calculate the m dot in your inner boundary, and a fraction of that is launched in the jet. And so this is how we joined forces. And also what I'm looking for in this talk paper is we're gonna sort of actually discuss these 2 main questions that were addressed by Noam and Ursula on Monday, and actually just a few minutes ago by Ryosuke and Hagai. And one is, how efficient is this m dot that's being accreted, and compared to the Bondy-Coyle Littleton accretion rate? And also, is the disk able to be created? And so hang on a while, we'll sort of discuss this. Okay, and so the global setup is, we took the red giant configuration identical to what Sagiv had. So it's nearly a 1 solar red giant. It has 83 solar radii. And so what we did here is we also incorporated the main sequence star, either when it's right close to the border, like the Grazing envelope evolution that Noam has already mentioned, and also we take when the main sequence star is already within the envelope, and so we analyze two moments: one when it's within, it just crossed the envelope, and then when it's way within. And so this is like the plunging, and just to be, so this is not PIB and PIB, so it's plunging, beginning, plunging, end. Okay, and so here's the mass and the of the main sequence star. And then what we also did is we launched jets. So we're either launching the jets when we're at the grazing stage, or we're launching the jets when we're at the beginning of the plunging, or when we are at the end of the plunging. And I hope Jesus Tuala isn't here, so he's not annoyed with this velocity for the jet. And we take a 30-degree opening angle. And so we take the luminosity of the jet consistently with what Sagiv used in his study. And we also take a luminosity which is self-regulated, and this depends on how much mass accretes in our inner boundary. This one is fixed at the Bondi-Hoyle-Littleton accretion rate at the outskirts of the envelope. Okay. Okay, and we're going to study like this small scale part. Right. So technical stuff, we use Fabio's 3D hydrodynamic Eulerian code. The simulations are performed in the rest frame of the main sequence star. In each of these three stages that we analyzed, we follow like 11 days. As I said, we take when we are in the border of the envelope, or when we are just crossed or so, and we are much within. And the jets will have different efficiencies. And it goes, of course, when no jets, up to really high efficiencies. Don't jump just yet, because we can justify this very large number in a while. Okay, and so we run 30 models and we analyze what happens. Right, so here I'm showing like the two representative successful jets, either, sorry, someone is scribbling. When we are in the outskirts, we see the meridional view and the equatorial view when we're in the outskirts, and also when we are in the beginning of the plunging. And here I'm showing, so you see these two nice jets formed here and also here. Okay, this is well. Okay, so when we're grazing, it's very easy to launch successful jets. They need around 10 to the 37 ergs per second. And yet, but we don't see a clear disk formed. When we are in the beginning of this plunging, launching successful jets is more difficult. You need higher efficiencies, independently if it's the constant powered jet, or if it's the self-regulated jet. Here, the jets need nearly 2 orders of magnitude more luminosity. And still, we do not see any clear accretion disk formed around the main sequence star. And when we are way within the envelope, absolutely no jet was able to be successfully launched. And they're all absolutely choked. And here, for this case, is when we went to ultra high efficiencies, 70%, and not even that. So it's just like to show like, not even going like onto unrealistic values, not even then. And so in our inner boundary, we calculated the accretion rate that crosses that border here. I'm showing for it's those 3 times. The lower one is when we are in the grazing phase. This one here is when we are in the beginning of the plunging, and this one here is when we are ending the plunging. And you see that it sort of goes up, and it starts from, say, 0.02, sorry, 10 to the 23, here 10 to the 24, and here around 10 to the 25 grams per second. And each of these are sort of within 1 to 5% of the correspondent Bondi-Hoyle accretion rate, which, by the way, is actually similar to what we had already seen in our previous studies, where we do have black holes and neutron stars involved within the common envelope, not this 0.3 main sequence star. And we also, what we also see is that the successful jets actually need an order of 2 or 3 times less power to be successful compared to the constantly powered ones. We also calculated the specific angular momentum that crosses the inner boundary. And this, unlike the accretion rate that does increase like a factor, an order of factor each time, here, it's always within 10 to the 18, 10 to the 18, 10 to the 18, which is around a third of the critical value to form an accretion disk. So this is why in our simulations we don't see a clear disk. And actually, it's actually very difficult to form a disk because our inner boundary is only around 3 times the size of the main sequence star. So to form that accretion rate from our inner boundary to where the surface of the main sequence star is, it's really, really difficult. So here we conclude that either the jet is pre-existent, like Noam already mentioned, and it survives all this journey, or we have these extra other mechanisms, just like Fritz showed in that beautiful simulation in which the jets are actually able to be launched just by MHD mechanisms and no disk is required. And also, I'm really, really looking forward to Hans' talk that he's going to sort of, I hope, discuss this. And so we conclude that, we follow this, the journey of this main sequence star through the envelope of the red giant descent spiral through 3D hydrodynamical simulations in which the jet are launched in these 3 specific times. We join forces with large-scale simulations that Sagiv and Roberto provided, and we saw that the jets are successful or drown depending on the jet efficiency and which of these evolutionary phase they are. If it's in the border, it's easy to launch a successful jet, and the further in you go into the common envelope, the more difficult it is. We see this mass accretion rate, 1 to 5% of the Bondi-Hoyle accretion rate. The specific angular momentum is around 1/3 of the critical angular momentum to see a disk being formed. And so having these large eta values, 0.7-ish or 0.3 even, if either we have a faster jet, or which is what I actually support is, if the jet is more collimated, so instead of having the 30 degrees, we have 10-degree jet, our eta would go from, it would reduce 10 times. So instead of having 0.7, we would have 0.07, only 7% of the mass that's been accreted is launched in the jet. Okay, and so last but not least, I have to say it's really nice to not be the odd one out. So normally I was with other common envelopers in high energy astrophysical meetings, and it was just a very few bunch of us. And now really, it's really stimulating and nice to see that this is a topic that's very interesting for more than just a bunch. And so I really thank Noam and Thomas for organizing this really, really nice and interesting conference. And so thank you very much.
Okay, Chagai, please ask your question here in the forum.
So I was asking two questions. One, the boundary condition is just right. It's just accrete, right? It's like a single particle.
Well, it depends. When we launch the jet, we have this cone in which the jet is launched, and all the rest of the 3D boundary, yes, it's accretion.
Okay, and the second question is, so what's the dependence on the accretion rate on the chosen inner radius? Did you try to check it, different inner radii?
Not in this study, but in our previous 3D studies where we have neutron star and black hole, we did follow that, and it doesn't change by more than a few.
But what? Well, you changed the radius by what factor? And how?
Yeah, we changed the radius to 1/2 and like to 1/3.
Okay, and the accretion changed by?
It didn't change too much. I don't want to lie, but it wasn't drastic. It wasn't. I mean, it was 50% at most. Like it didn't really change the order of magnitude of the accretion rate. We also found like 10 to the 25 grams per second.
What I am worried about is that you change a factor of 2 and you get a factor of 2. That's not too bad. The problem is that we have a few orders of magnitude before we get to the energy, the region where we actually can dissipate energy through, for example, neutrino cooling.
Yeah.
So if, for example, if it's just linear, okay, which we don't know, but if it was linear, then we get almost nothing, okay, in terms of accretion. This is why I'm worried even by a factor of 2 in that sense.
Yeah. I mean, here the problem is, even though we are able to solve nicely the jet, if we go too further in, then the pixels are not.
No, I understand the complexity. Of course, I understand the complexity. It's the resolution is really a problem. I just kind of continuing my line of we need to be very careful with the assumptions about accretion. And already what you find is like 0.1 to 5%.
Yeah,
that is already strange. If you just assume Bondi Hoyle, why should you have so far less than that? Okay,
because we actually have more wind accretion here.
Yeah, it's not. It's already not following a very simple Bondi Hoyle or even 10%. Okay, you get even 0.1% is 2 orders of magnitude below 10%, for example.
Yeah.
Already in this very large inner radius, not even close to the small radius. This is basically my point that I raised earlier, and I don't say what you're showing shows this, but it's also making me be more. I think it's an important caveat to consider in all this. That's all.
Okay, Rai, please.
Yeah, so I have first a technical question. So how do you define the Bondi Hoyle accretion rate, like when you're outside the star? Like, are you using the density of like the surface of the star or something?
Exactly. Yeah, so we use the as you say, the density in the border and the Keplerian velocity, and with that you can calculate the Bondi Hoyle accretion rate.
Yes. Okay. So my second question is, I still can't get my head around like how you launch a jet from a main sequence star. Like, what's the mechanism? Is it like a Blandford-Payne-like thing, or like what kind of mechanism do you need to collimate the flow upwards?
Young stellar objects do it happily.
What's the mechanism there?
MHD from a disk. I mean, the idea is that's why the question of the disk matters so much, because you can easily launch a magnetocentrifugal jet from a main sequence object with a disk around it.
So it's basically like a Blandford-Payne mechanism.
Yeah. A fling mechanism. There's also the possibility of spring. I mean, if you wind up the field enough, you can get a very different mechanism, what they call magnetic tower. But either way, if you've got a differential rotation close to the star with with a main sequence star, you can launch it.
And there's actually another mechanism that Noam studied like this. If you have an accretion belt surrounding the main sequence star, you can also sort of launch a jet. And also, there's even a sort of more exotic model followed by a student of mine, Alejandro Aguayo, that he's seeing that if you simply have like a density gradient and you have infall, you can launch a wind-ish.
Adam, your question.
Yeah, I just wanted to talk more about the subgrid model for accretion, because we've certainly found that matters a lot. You can get very different results about whether you're just sort of taking mass out or whether you're taking mass and pressure out. So, and I think this is a real something that could, is worth studying a lot more, because those subgrid models for accretion can have a difference. So what are you using? And
here, the material that crosses completely disappears: mass, pressure, energy.
Right. Okay. That might be something worth playing with, because I really like your approach. This is a great paper, because I think, that, being able to just focus on particular domains just to see what can form. But those, because there's like, there's like in the Young Stellar Object Committee, there's a Young Stellar Community, there's 3 or 4 dominant models that people have put together. And what we found is that you get different answers depending on what that, which one you use. Or there can be different answers. One has to be careful about or think about it.
Okay, we will have discussion at the end of the day. So we will meet at the hour plus 20, each one with its own hour. So in 9 minutes, we will.
No.
Okay.
Hold on, let's take a group picture now. Since we still have 70 people, we can take a group picture. So everyone, please put your face on, switch your camera on for a moment. I'm gonna make the screenshot in a second. Everyone ready?
Some people.
Noam, you can talk about jets now. You have extra minute now to do this. So I have to do it multiple times because there's so many of you.
Yes.
And the last one. All right, thank you very much.
Amy, please.
Okay, so hi everybody, my name is Amy Yang Shinzo. I'm a grad student at the University of Rochester, and today I'll tell you about our simulations involving jets in common envelope evolutions. And my collaborator here based at the University of Rochester, and you will also hear Luke Tremondy presenting this afternoon, so stay tuned for the talk. So it's why we started JET, because we know the companion in a common envelope system can accrete from the envelope material before or during the common envelope evolution. And the previous models involving accretion on the subgrid scales show that the accretion can happen at a rate or above the Eddington accretion rate. So if we take a fraction of the accreted mass and feedback that energy into a bipolar jet, that kind of energy could transform the energy back into the envelope and help envelope unbinding. The first kind of 3D global simulation involving a jet was done in 2019 by Schreiber and collaborators, and they found that jet increased the outflow flux of material. So here we conduct a set of 3D global simulations where the secondary also launches a jet, and we only do a very early stage of the common envelope phase. So we simulate about 10 orbits, which last for 40 days. So here's our model setup. We use the AMR code Astra Bear. We have a primary star, which is a RGB star with 2 solar mass. In total, so it's the same setup as Luke studied in 2018. And the secondary is a point particle in the simulation. So here represented with this green dot. It's roughly 1 solar mass, and we try to simulate take it as a main sequence star for now, and have it launch as a jet, bipolar jet in the up and down polar directions. In most of our models presented today, the secondary will lose this mass to power this constant mass loss rate in the jet. And And the feedback simulation is like we assume there's a subgrid accretion disk already forming around the secondary star, but like we do not explicitly include accretion of any gas here. And the initial orbital separation is about 49 solar radii, so it's slightly above the radius of the RGB star, the primary star. And for the jet model, it's primarily based on the work by Federas et al. So here we have a 15-degree opening angle of the jet launching region, which lies inside the softening radius of the secondary particle, and we smooth the density and velocity distribution of the jet over the angular distribution, and also there's a smoothing function in the radial distribution. So in the figure, you can just see a normalized profile of our jet speed in the angular dependence in the jet launching region. And we take the velocity of the jet to be a factor of the multiple of the escape velocity. The Q efficient is either 2 or 4 in our model. And we assume the secondary to be 1 solar mass mean sequence star. And our fiducial setting, we set the jet mass loss rate to be equal to the Addington rate, so which is 2 times 10 to the minus 3 solar mass per year. We assume the accretion rate to be equal or less than about 10 times the Addington rate, and with a feedback efficiency at 0.1. That's why we choose our jet mass loss rate to be the Addington rate of a main sequence star. And our jet subgrid model does not remove any mass from the simulation. So mass and momentum, we try to conserve those mass and momentum in our simulation. So here's 5 of our rounds. So basically we compare the situation with jet and no jet. And so our fiducial is J1, is where we take mass from the secondary to power the jet. And in J6, it studied the effect of doubling the jet speed. And J7, we're just testing the subgrid model of the jet launching, and we're doubling the jet launching angle just to test the effect of the jet model. So here you can see the time evolution of the interparticle separation of the 5 models shown in the last slide. So the first message is the jet doesn't contribute much to the orbital evolution. You don't see any significant difference, but you do see if we focus on this green solid line, which is our fiducial model, and compared to the red dash curve, you see a phase shift, and roughly all the model with jet ends up with a slightly smaller orbital separation at the end of the 40-day period. If you look at the inset, it shows the entire orbital evolution of the 40 days, because before day 10, all the models overlap. And even though we put our jet, our companion, just slightly beyond the RGB star, is still plunging very fast. So here we take a close look at our fiducial model, J1. Here in the movie, you can see there's a pseudo-color rendering of only the jet material. And here we're sitting at the perspective of the primary core, and we're looking at the secondary, the companion star. So the small green circle in the middle of this figure is representing the softening radius of the companion particle. And you can see at the beginning of the simulation, I'll just wait for a second. Yeah, you can see the jet launches in the bipolar shape. And before the first periastron passage, around day 11, day 12, the jet gets deformed, bended, and eventually quenched. And later time, the jet could not make out of the envelope, and you see just this ellipsoid around the secondary. We also do the estimation by balancing the ramp pressure and the gravitational force, and our calculation that the jet should be quenched around 9 days, which agrees roughly with the simulation. And here is still we're at the same perspective, but this is a time sequence showing the evolution of the total gas density. And the first row is the model with jet, and the bottom row is the model without a jet. So you see the plunging phase, you can clearly see the jet is clearing out the envelope and trying to form a bipolar jet at first few days, and at day 6, in the second panel, you already see the jet being bent by the envelope, and around day 10, it's really get deformed, and the jet quenches before the first period passage, and it never breaks out in this model. And later on, the simulation with or without jet just looks very similar in the flow pattern. So that's where we end in day 40. You can see some slightly difference in day 40, but it's just because the orbital phase are slightly shifted. Yeah, and we're also looking at the mass unbinding in our model. So the top panel, which shows the unbound mass in the entire simulation domain, you can see the general trend is there's not much difference between the jet model and the no jet model. The maximum unbound mass happened slightly later, but still around the first period passage. And the bottom panel is we take the difference between the jet model and the no jet model. And I want to point out is this light blue sine curve, which is almost a horizontal line, but that's the sum of all the jet materials we pump into the simulation. And you can see the model with involving a jet, definitely the jet facilitate more envelope material to unbind, even though it's a very little amount, but still it's significantly more than the jet material we injected into the simulation. So it's the envelope material that's being stirred by this jet, by this external jet, and more material start to unbinding during the simulation. So our main message is that the effect of jet is quite small, but we still see the jet quench at first period passage, and does not affect much of the common envelope morphology or orbital evolution, and as well as the mass unbinding. But we do see, like in point 3, that mass unbinding increases slightly for the models involving jet, and the time and behavior of jet quenching agree with our theoretical estimation. We have explored a set of parameters like jet speed, opening angle, companion mass, accretion rate, and jet mass loss rate. Qualitatively speaking, our results are insensitive to these parameters. The ongoing study we're looking at is the effect of accretion onto the companion, and we will in the future also study the case of a white dwarf or a neutron star companion. And if I can have one more minute, I want to show you a preliminary look at the model with boundary accretion. So it's the same fiducial model we just looked at, but now we add a boundary accretion to the secondary. So the secondary accretes from the environment and also powers the same jet. And here in the snapshot, you see this density evolution in snapshot in the same time sequence, and it's still at the early stage we see a very strong jet, but later on the jet gets quenched, and because our accretion is very strong, as you can see here, on the right figure is our secondary mass. It accretes a lot after the first periastron passage, just we set it to accrete at its local boundary Hartley turn rate. So because it accretes a lot, it clears out its environment, and at later stage, we can see the jet breaks out again. So we wait and staring at the left panel. Later on, this is only the jet density. Yeah, you see the jet starting to clear out at the top, and then at the very last, just the last second, it starts to breaks out also in the bottom polar direction. Can wait to see it happening again. Yeah, so right now it starts to clear out in upward and then downward. Yeah, and that's because if we measure the instant accretion rate onto our companion, we can see this blue curve, it's really like 100,000 times above our jet mass loss rate. So it's like the dominant factor here is the accretion. And if we see the total gas density, I would compare at the end of our simulation with accretion, we can see the secondary really clears a funnel shape around it in the polar direction compared to the no accretion model. Yeah, so that's how the accretion could make a difference, but we need to continue the study of this accretion models. So, okay, so I think I'm beyond time, so happy to stop here and take any questions. Thank you.
Okay, well, questions, answers. What is the difference in the last simulation that you just showed? What is the difference between the previous one? You just assume accretion, or the power of the jet depends on the accretion rate?
No, we fixed the power of jet, but the companion particle is free to accrete from its local environment on the instant boundary rate.
But you didn't follow the companion if it expands upon accretion or something. You assume it's a point.
No, the companion is a point particle, so its mass increases when it accretes, and it also power this fixed power jet. Yeah, we're trying to do another model with a fixed feedback rate, and so the jet power would be depending on the accretion rate. That would be a future work.
Okay, very nice. More points. Yes, Alexei, please.
So I'm curious because I recall also just a few days ago we had a talk by Fritz Röpke about MHD simulations of common envelopes, wherein the in spiral leads to amplification of magnetic fields and launching a powerful outflow, which is actually not quenched. I mean, can you comment on how that power of such an outflow you imagine could relate to the jet CO model? So would the dominant? I mean, I'm trying to basically ask if the dominant feedback mechanism would be due to the jet launched like that from near the accretor, or through the kind of binary interaction which Fritz was talking about.
I have very little knowledge about magnetic launching. So here in our model, we just assume there was some subgrid mechanism to power the jet.
Mm-hmm. Maybe Fritz could comment on that. Sorry, just because Fritz is in the audience. So,
I mean, I think in these models, we're assuming there's some mechanism, and most likely, I mean, in our heads, at least when we build it, we're assuming that it's going to be some kind of MHD launching from a disk, right? Because that's sort of the standard way. You know, if you get accretion disks, you can get that's the thinking. But I think in some sense we'd be agnostic to the jets are coming from the secondary, and that's however you're doing it. In these models. The thing that's interesting, though, I mean, to me, in these, the last results that Amy showed is that it's possible, and I think this requires a lot more work. It's possible that even though you quench early on, but this is why the modeling the accretion is so important. The accretion can suck out enough material or clear a space that actually later on the jets can be unquenched. And I think, I mean, that's a huge question, I think. But as usual, the most interesting thing in the simulation happens right before it ends. So, if we see that continue, I think that'll be an important result for the community. So.
Fritz?
Yes, just to comment on our simulations. So in our simulations, actually the jet launching happens very late at a time when the envelope is already more or less gone, almost 100% ejected already. So therefore the jet also doesn't quench because there's not so much material there anymore. It propagates along this chimney, and that's rather low density material. So that's the main difference here. And of course, the launching mechanism, that's something that comes out naturally in our simulation, so we don't set it in. But it's not around the companion star, and it's not happening in the early phases as in Amy's simulation.
Yeah, so in our simulation, we turn on the jet at the beginning of the simulation and just plunging very fast into the dense envelope.
Okay. No more question, please. Shlomi, you're the next. Please share your screen. Okay, Shlomi Hillel, please go ahead.
Thank you. So this is joint work with Ron Schreier, Sagib Shiber, and Noam Soker. The scenario in our project is of a neutron star orbiting inside the envelope of a red supergiant and launching jets. First, we explore the morphology of the ejected envelope. Second, we investigate the negative feedback mechanism, where the jets reduce the accretion rate onto the neutron star. And the results will also be applicable to black holes. Here's the top view and a side view of our scenario. The motivation for the project is first, LIGO shows that there are many close binaries of neutron stars or black holes. Many might result from common envelope evolution. We expect the neutron star or black hole to accrete mass and launch jets during the common envelope evolution. Second, there are peculiar energetic supernovae, some of which might be common envelope jet supernovae. Here's the numerical setup. We begin by evolving the red supergiant using MESA, a one-dimensional code, and then install it in Flash, a three-dimensional code. The inner 20% of the stellar radius is an inert core, where we hold the hydrodynamic variables fixed. We do this for numerical reasons. And then we insert the jets. We assume that the neutron star follows a circular orbit. We do expect the neutron star to spiral in, but in this work we simplify and just use a circular orbit. The jets have a half opening angle of 30 degrees for the jet interaction regions. This is not the original jets, but the regions of interaction. In any case, we cannot resolve the jets. And we model them by some subgrid physics. The jet power is determined by factor zeta of the Bondi-Hoyle-Littleton accretion power. I will have more to say about that later. For the simulation I'm about to show you, we use zeta equals 10 to the minus 5. We include radiation pressure, but not self-gravity. There is only the potential of the red supergiant, and it is held fixed. Without jets, the star would be in hydrostatic equilibrium. Let me show you some results. Here's the evolution in the equatorial plane where the neutron star orbits. Here's a close-up at a particular time during the first orbit. And the arrows show the velocity. And here's the meridional plane where you can see the jets at the beginning of the simulation, after half an orbit, and after a full orbit. Let me show you two movies. Here again is the evolution in the equatorial plane. As you can see, the neutron star orbits counterclockwise in the envelope of the red supergiant. Show the movie again. So what we see here is a slice in the equatorial plane with a color map of density in logarithmic scale. This movie is of the first full evolution. In the simulation, we continue for a few more evolutions. And here's a 3D movie showing two isosurfaces of density, one highlighting the jets and one highlighting the envelope. Let's watch it again. So the whole effect here is by jets. There is no self-gravity, as I said. We'll now move on to the second part of our project, the negative feedback mechanism. This is actually still work in progress. The jet power is determined by three-dimensionless factors. Chi-j is the factor of reduced density due to the jet activity. Xi is the factor going from the Bondi-Hoyle-Littleton accretion rate to the actual mass accretion rate. And eta is the factor from the accretion rate to the jet output. The product of this factor is zeta, which determines the jet power. So again, when compared to the unperturbed Bondi-Hoyle-Littleton mass accretion rate, Chi-j is the reduction in the density which goes into the formula. The mass accretion rate is proportional to the ambient density. Xi characterizes the fact that the Bondi-Hoyle-Littleton accretion rate is not completely appropriate here. For one thing, angular momentum doesn't figure into that model, and there are other issues, as was already discussed in this session. And then eta is the efficiency of the jets. That is the factor going from the accretion power to the jet power. And zeta is the product of these factors. This was all discussed by Noam at the beginning of the session. So now the idea is that if we fix a value for the product of Xi and eta, then the Chi-j can be determined from a kind of self-consistency condition. On the one hand, Chi-j determines zeta, and so the jet power. On the other hand, the jet power determines through a simulation the reduction in the density, that is Chi-j. If we get the same value as the one that we put in, then we're in a self-consistent situation. Here's a graph showing the evolution of the density at the distance of the Newton star. This one is for a simulation with no jets at all for comparison. It should be constant, but there is some variation due to numerics. But the value of the density returns to its original value after some time. Here are three more graphs for three different values of zeta. We see that, as expected, the higher the jet power, the more severe the reduction in the density. We plot this here. Note that even for the lower end of Xi eta, zeta must be only 100 times smaller than Chi-j, which is the y-axis here. For the higher end of Xi eta, zeta will have to be only 20 times smaller than Chi-j. These are just rough estimates, but it does appear that to achieve the condition of self-consistency, we have to go to higher jet powers than we show here. This is what we are trying to do at the moment, but the simulations are becoming much more computationally intensive. So let's summarize. Just that Newton stars launch cause complicated envelope evolution. They might account for peculiar explosions. They can cause an efficiency alpha greater than 1, and they reduce mass accretion by negative feedback. Thanks for listening.
Thank you, Shlomi, for this talk. Yes, please, comments. Luke.
Yeah, I was just wondering, you showed a movie of the simulation. I don't think you showed the one without the jet, right? So how do they look? Do they look very different, or does the one without the jet also unbind very quickly? And the second thing is, it just seems like your jets have a huge effect on the envelope, and it seems to me that it's very different from what was presented by Diego. And is there any reason why? Like, is it the parameters or the model? What do you have any clue as to why that might be?
Yeah, so As to the first question, the simulation with no jets at all are almost stable, but the instability arises only after the time scale of the orbits here. So
no, he asked simulation without jet. We don't have in the simulation any gravity, no self-gravity of the envelope, no gravity of the neutron star. So without jet, it simply lets the star relax, and this is the question and the answer are not the same.
So maybe I didn't understand. Sorry.
Huh? Yes. No. Look, you asked what the simulation of the neutron star inside the envelope without jets.
Right.
But we have no gravity of the neutron star, so we look only on the effect of the jets.
I see. Okay, thank you.
Yeah.
This is the question. Shlomi, you refer to the numerical instability.
Yeah.
Okay.
And I'm not sure about the second question. No, do you have any comment?
No, we use neutron star. I don't think Diego has a neutron star, but a main sequence one. Maybe Diego can say something.
Yeah, but in our previous studies, we do have neutron star in the common.
From the outside, starting from the outside?
No, deep within the common envelope.
Yeah, okay. So it's not the same as the simulations you showed today.
Oh, no. Today is main sequence. But yeah, in our previous studies, we do have the compact object, but within.
But you said today is main sequence, but what differentiates those? Because it's a point particle anyway, and you're using some 10 to the 6 times the Eddington rate. So I would think that would be more appropriate for a neutron star or a black hole.
You're asking, well, in our previous, like the main difference is the velocity of the jet. In the others, it's 1/3 of c, and here it's only 400 kilometers per second. And yeah, that's basically like one of the biggest changes. And of course, the gravitational force of the point mass.
How big was the point mass?
In the previous ones or in this one?
In this one.
0.3 solar mass.
Thank you.
Yes, the velocity of the jet is different. The potential well of the neutron star in the main sequence is 5 orders of magnitude. So. Yes. Tomek, please.
So if this model is correct, does it mean that Thorne-Zhitkov objects do not exist?
This is what we claimed in earlier paper, that you cannot form such object with a neutron star from outside. Some other model, maybe even Haji can comment on that, say that if you have a white dwarf coming in, accrete mass, and then suffers accretion-induced collapse, then you form a neutron star in the center. So this is a different scenario. I'm not sure it can happen because of the release of energy. But we think that if you have a neutron star spiraling in, you will not form Thorne-Zhitkov objects because of the jets. Yes, this is our view.
I see, thanks.
More comments? If not, Ron, please, last speaker of this session. We will continue this session a little bit longer and we'll have a little bit shorter break, but this is the last day, so you can sleep all day tomorrow.
Just a minute, I will share my screen. Okay, can you see my screen?
Yes.
Okay, so hello everyone. In this talk, I will describe simulations of a rare event of a supernova imposter. My name is Ron, and my colleagues Shlomi and Sagiv are collaborating with Noam Soker for almost a decade now. So what is the scenario we are studying here? We're talking about a tertiary star on a white orbit which perturbs a neutron star and a red supergiant inner binary. And the perturbation sends the neutron star to orbit inside the envelope of the red supergiant. Just a minute. Okay, so this neutron star at the beginning moved in a circular orbit around the giant, and due to the perturbation, it changed its course to have very highly elliptic orbit and plunges into the giant. So the giant itself is about 881 solar radii. The neutron star itself has a periastron of 400 solar radii and upastron of 6,400 solar radii, so the eccentricity is very high. The orbital period is almost 17 years, from which only half a year it travels through the envelope. Once the neutron star enters the envelope, it accretes mass and starts to emit two conical jets at opposite sides. And when it leaves the envelope, it stops emitting the jets. What's the motivation? There were several observations that indicated the existence of peculiar gap events, those who have luminosity between that of classical novae and supernovae. Some of them might be common envelope jet supernova imposters. We expect that instabilities in some evolved triple star systems lead to a neutron star moving inside a red supergiant. So what's the secret recipe for making such a simulation? We start with a 1D profile from the MESA code. We took that of the 12.5 solar masses red supergiant with a radius of almost 900 solar radii and metallicity of 2%. We expand the 1D profile to be 3D profile in the flash code. In order to avoid small time steps, the inner 20% of the star, we make it inert, which means we do not change the density, the pressure, and the temperature there, but we do not change the gravitational potential of the original star. The neutron star itself is 1.4 solar masses, as I showed before, at highly elliptic orbit. We do not include the self-gravity of the neutron star or the perturbed envelope. We consider it to be a minor effect, and we do not take into consideration convective motions inside the envelope of the giant. So as I showed before, there are two jets, opposite jets. The jet envelope interaction has a half opening angle of 30 degrees, and the jets are active only while they are inside the neutron star envelope, and they are time dependent, which means they start at a certain power and increase the power up to the periastron, and then back again when they leave out, they reduce the power, and now they stop launching jets at all. As Shlomi said before, we set zeta to be the power, the ratio of the power of the two jets to the maximum Bondi-Hoyle-Littleton power that's here in the where we are in periastron. We do take radiation pressure into account. Otherwise, we will get non-physical temperatures higher than 1,000,000 degrees and things like that. So first, I will show you two movies of the results. As Shlomi did before, the first one is at the equatorial plane. These are density movies. I will start it again in a moment, just to so that you will get the impression. I'm starting it again. So you can see that the jets move at the elliptical orbit, and soon they will be at periastron. And at the beginning, we have a huge outflow opposite to the direction of the entrance. Now the jets do not longer exist, but still a lot of flow is going out of the envelope in the direction of the outbound of the trajectory because of the huge mass that was invested in the star, in the giant. Okay, the second movie is a 3D movie with two colors. The purple color emphasizes the core and the two jets. You can see the lower part and the upper part. Here are the jets. I will start it again. And the blue color emphasizes the expanding envelope. So at this stage, you can see the jets. They will appear at the other side. And now they do not any longer exist, but still the envelope keep on expanding for a long period after the jets have disappeared. Okay, so if we take a closer look at the equatorial plane, at the densities, on top of them velocity vectors, we see the flow, which is clumpy and inhomogeneous, opposite the direction of the entrance of the neutron star. This is only 23 days after beginning. Let me remind you that it takes 6 months for the neutron star to leave the envelope. We are now 2.3 months after the beginning, 3.4 months after we are a little bit after periastron, and now we are 8 months after beginning of simulations. The jets are not active anymore, but still you see a huge outflow opposite to at the direction of the outbound. 1 year after the beginning, and only 3 years after the beginning of the jets, you see that the star begins to relax to some kind of stability as it was at the beginning of the simulation. If we are looking at the density maps in the meridional plane, this is the equator, we see up-down symmetry, but no more than that. We see huge flow opposite to the entrance of the neutron star, 35 days after the beginning, and 8 months after the beginning, we see a huge outflow on the outbound of the neutron star. Again, the flow is very clumpy. Another important, view, nice view to look at is at the velocity map. You see here that different parcels of gas, for example, that one and that one, move at different velocities. So the faster will catch the slower parcel, they will collide and convert kinetic energy to thermal energy. And for us, it's very important because we want to observe this phenomena and we will be able through the thermal energy. We were trying to make a crude assumption, a crude estimation of how the light curve look like. So we figured that the emission from this phenomena will come from two components, the thermal energy and the recombination mainly of the hydrogen. So we combined them and we saw that the estimated light curve is very bumpy. There are mainly two bumps, one a little bit after the beginning of the plunging of the neutron star, and the other one is a little bit before, just before the neutron star leaves the giant, the envelope of the giant. So, for example, in this simulation where zeta, the ratio of the jet's power to the maximum Bondi-Hoyle-Littleton power is 10 to the minus 4, the total jet's energy is almost 2 times 10 to the 49 ergs, and about 4% of it is estimated to be radiated. Another interesting result is that more than 2 solar masses out of the 12.5 at the beginning left the grid as unbound mass. So let me summarize. We simulated a long-lasting transient, that one which lasts for several months up to a few years. We found the morphology, the outflow morphology, to be very complicated, not without any symmetry almost. The estimated light curve was very bumpy, and we find no symmetrical outflow. And the phenomena, this phenomena might repeat itself next time the neutron star is at periastron. So I leave it here. I just wanted to, there was a question before about the simulation of the simulation without any jets. So we see patterns that are familiar, that are due to the grid itself. But actually, even for a long time, no mass leaves the grid. We took it for a long time, and no mass left the grid. The giant itself is not spherical anymore after a long time, but that's reasonable with such simulations. That's for Luke, for his first question before. That's it.
Yeah, thank you. But again, the question of Luke, when you say without jet, you mean no neutron star, nothing. What Luke was referring to was what happens if you simulate the neutron star with its gravity through the red supergiant. But this we did not do. We looked only on the role of jets.
Mm-hmm.
Amit, please. Amit, are you talking? We don't hear you.
No.
Yeah.
Can you hear me now?
Yes.
Okay. So you mentioned that the flow is clumpy. Do you know why exactly it's clumpy? Is it related to instability or cooling or what?
Just because it's directional. It comes from one direction. That's all. Otherwise, it will be because it's a point mass almost that enters the envelope. As you saw in the meridional plane, you can see up-down symmetry, but it's clumpy because it enters at a certain point and then leaves at another point, and it's not simultaneous. So one at the beginning you will see it from one direction, and at the end you will see it from another direction. That's why.
But the question is, Amit asked why you have clumps. It's not smooth. I think it goes with interaction of jet. You see it in cluster of galaxy simulations that Shlomi did in his PhD, that whenever you launch jets into an ambient medium, you get vortices. And those vortices suffers Kelvin-Helmholtz and so other instability. So we get many vortices in the jet envelope interaction, and these influence outflow. This is my view of small-scale clumps. But Ron is correct that it's not symmetric. The entrance and exit are not symmetric, and this also adds to the complication of the flow.
Thanks.
But the basic clumps, and I think the jet ambient medium interaction, always we see vortices on the sides.
Okay.
Ila, please.
So I had some connection problems, so I hope that I didn't miss anything. But so my question is, if you looked at how the power of the jets, their accretion rate, and so on, how they did actually affect the onset of the common envelope? Because if you initiate the common envelope with a very eccentric orbit, then perhaps you add some orbit that also throws some mass before the spiraling began. So did you actually test it? Did you see this effect?
If I understand you correctly, actually what Shlomi showed before is a different different scenario in which the neutron star moves at a circular orbit. So we did also several simulations with circular orbit with different powers, and it looks completely different. In this simulation, there is two main events: the entrance and the exit of the neutron star, and it's very different from the scenario where it moves, where the neutron star moves at a circular orbit around the center of the giant.
No, the question.
That's why I asked. So I asked if you looked at the exit in the first orbit, that you entered the envelope and then you had a part of the orbit outside again. So did you look at how much mass did it accrete during this first orbit inside the envelope, and how was it affected by the power of the jets?
Yes, we took several scenarios, and we took several simulations, and we found how the mass that leaves out changes. So it's very different if you take different zetas, then you will get different outbound mass coming out of the giant. In the first three simulations, it will be very difficult to observe them through observations, whereas only in the two last simulations we have enough mass and enough power to observe them, I think. I hope I answered your question.
Yeah, thank you.
Any more? Yes, Aldana, please.
So if there are not any more direct question towards Shlomi, I wanted maybe to emphasize, because they use the parameter zeta in the calculations, it has a crucial role. So I prepared a slide maybe to emphasize how we obtained zeta in the first place.
Okay, so Ron, maybe you unshared your screen, and Aldana, do you want to share screen?
Yeah. So like Noam showed before, the parameter zeta is the ratio of the accretion rate, actual accretion rate of by the compact object to the Bondi-Hoyle-Littleton mass accretion rate. It is composed of the efficiency parameter eta of the energy that goes to the jet, the percentage of the Bondi-Hoyle-Littleton mass accretion rate that is taken from simulations, and we also add the negative jet feedback coefficient. And so what we actually do is that we inject a value of zeta times the Bondi-Hoyle-Littleton mass accretion rate in the form of energy to the envelope, and we find where we have a self-consistent value of the negative jet coefficient high jet, which is equal to the density of the perturbed and the unperturbed envelope at the same times. So we get this graph over here for two simulations of a neutron star inside a red supergiant, when the left panel shows the results for several radii in which we compare the ratio of the densities for neutron star dispersing until 100 solar radii, and the right panel for neutron star spiraling deeper down to 20 solar radii. So we present the value of eta times zeta, a function of chi, and see, and we infer what could be the value of chi for our specific simulation, which gives a self-consistent solution. It was clear.
Yes. So yeah, I would add that this simulation was done with mass, assuming that the jet power is distributing spherically symmetric, because this is MESA model. But what Shlomi Hillel showed was simulation with jet in 3-dimensional. This is why he had a very hard time to simulate high power. And in this simulation, yes, this is in 1D, and usually, as you showed, we take eta, the coefficient, to be 0.1 or 0.2, and the ratio of accretion to psi, accretion to Bondi Hole, to be 0.1 to 0.5. And so the values are from here, typical value, something from here to a little bit higher, this region, say, the best. And we demand that the power that we take will be consistent with the reduction of density due to jets. And we find these values. So in addition to the reduction in power due to that, the Bondi Hole little analytical value is supposed to be 20 or 10% even lower than the Bondi Hole analytical one. Also, the jets remove mass. And actually, these results are consistent with the results that Shlomi showed, because he didn't get yet into this because of numerical difficulties. The simulation is long. But we find typically that the jets remove mass and reduces the energy at about a factor of 10 relative to the unperturbed envelope. But again, there are several uncertainties. But this is spherically symmetric, what you say. You should emphasize it. Because, Shlomi, yes.
So this also relates to Hagai's point regarding the accretion rate, that it should maybe look more carefully at the accretion rate, because here we have another effect, additional to the effect we took in the model of the neutrinos, because there we did not include yet the effect of the jet feedback mechanism and the reduction of the accretion rate by high jet. So the accretion rate is a matter we need to look very carefully at.
Yes, more comments. We open the discussion now, and we can go a little bit further with the discussion. It's open to any comments to this morning or to this meeting or whatever. And then we will go to a break of 30 minutes and reconvene. So we have some time 15 minutes to discuss. Please. Yes, Adam, you start, and then Bruce.
I guess so. It seems like maybe we're heading towards maybe a consensus that the jets, at least in the early phases, may not matter. I mean, it depends on for jets for other than neutron stars. It's not clear yet whether, we're heading towards the fact that jets that they get quenched, and initially they don't play a stronger role as we thought they might. However, at a little bit later times, if what Amy is seeing in our simulations, and then also the work of Fritz at later times, it's possible that the jets re-energize in terms of their impact on the outflows. I'm wondering if that's what, other than neutron stars, is that where we're headed? Question. I'll stop there.
My answer is no, I don't. I think jets are important. Depends what you are looking for. Because remember, in many cases, most of the energy can go to inflate envelope and you don't see anything. So if the jets are outside, like in the grazing envelope evolution, they might power radiation by collision with circumstellar material. So it depends. Also, black hole is also important as neutron star. White dwarf, I agree. Not main sequence, I think, can give you accretion, as I said before at the entrance to the common envelope and the exit from the common envelope. So I would not dismiss the jet yet.
I ask actually just before I'll leave it alone. But what about the interaction between the jets and the recombination energy? Can the jets inflate things enough that where we thought recombination energy might play a role, it would actually allow it to? I know you don't believe in recombination, but I'm wondering.
Not believe. I think most of it, some of it can be used to unbind envelope or accelerate it. But I think most of it actually is radiated away, mainly the hydrogen combination. energy.
The jets might help that. If the jets really inflate the envelope, then they would lower the density of the envelope and they would contribute to that process.
Bruce? Bruce Bali.
All right. I have two statements, not questions. Number one, if you listen to planetary nebulae, if you believe that they're telling something about the mass loss process in a common envelope, then you have to produce sustained winds long afterward. And on occasion, you have to make jets, both of them. Those are conditions for common envelopes and planetaries. My second statement is really a statement of appreciation and thanks to Noam and Tom and everybody else who set up this meeting. I really think everything has gone perfectly. I've enjoyed this meeting immensely, and I want to thank, and I think we should all clap and thank the organizers before the break, because a lot of people are going to drop off, I fear.
Thank you very much. Okay. So, Alexei, please, your turn.
Right. Well, I had a science question. So, well, we talked about jets quite a lot, and well, if you think about neutron star black hole accretors, then we also know that the Eddington mass transfer rate is determined by the fact that radiation counters the gravity force classically. So I mean, the question is perhaps how would we expect the contribution of the feedback would be from radiation and from jets? So like, what would be more important, what would be less important for neutron stars and black holes?
Everything is optically thick. Radiation doesn't play a role when you have neutrino cooling around the black hole and a neutron star. Black hole can also accrete material. The jets take 10%, maybe 5% of the energy, maybe 20%, so 10%. So radiation is tricky. Eddington luminosity, remember, Eddington luminosity has two big assumptions, spherically symmetric and optically thin. And we must remember it. Here it's neither of the two. It's not spherically symmetric. You have accretion disk because of angular momentum, and it's optically thick. So Eddington limit is not so relevant.
No, but the mass transfer rates are well above Eddington. So I'm just saying that Eddington is just a good scale where the radiation starts to become important.
Yes, radiation pressure you must include in the simulation, say, and so on. But yeah, yes, you need to include it in the equation of state, but radiation cannot escape. This is one of the problems. Say if you go to cluster of galaxy or galaxy formation, if you want a feedback from the active galactic nucleus, you have a problem with radiation because it's opaque. The moment it's transparent, radiation escapes. So you cannot actually, radiation cannot transfer energy to a long distance. Either it's opaque and the moment it's transparent, it escapes. Jets, on the other hand, continuously interact with the interstellar or intracluster medium or the envelope. So this is why I prefer jets and not radiation.
No, that's fine. Can I just last formulation of the question? So has anybody simulated the energy input from radiation? Because radiation indeed heats up the region near the neutron star, and that heat probably then affects the rest of the pressures. I mean, has anybody tried to simulate that, and what is the relative contribution from the two after all? Or maybe nobody has simulated that. I mean,
if you look, people simulating core collapse supernovae, so the entire core collapses to the neutron star. You have a shock at 100 kilometers, and then radiation is, I mean, photons are important. They supply the pressure, but the game is with neutrinos and so on. So they escape. So the neutrinos play the role of radiation in usual cases. This is how we see it, but of course you need to include photons in the equation of state and so on. Yeah, more comments and anything. If there are no comments anymore, we will do and we will reconvene at the planned time. it will be 38 minutes. So thank you. Alexa, you have more comments, or it's with previews?
No, it's just a remaining hand, sorry.
Okay. So we will meet at, in 38 minutes. Please take a break for the last session. Thank you very much.